Hello dear participant and welcome back the today's new lecture on why matrix algebra for artificial neural network and the machine learning. Without mathematics, artificial intelligence is imagination, and with mathematics it becomes innovation, rightly said. AI often feels like magic, machine recognizing faces, understanding language, and making predictions. But behind this magic is mathematics working quietly and precisely. In artificial neural network and the machine learning, matrix algebra is the backbone. Data is stored in the matrix and model weight are the matrices, and learning happens through simple matrix operations like multiplication, addition. These operations allows machines to process large amount of the data quickly and learn patterns efficiently. Without matrix algebra, AI would remain just an data or idea. With it, AI becomes real, reliable, and useful. So in this lecture, we will understand why matrix algebra is essential for artificial neural network and the machine learning, and how mastering it help you truly understand how intelligent system learn and work. So here we have the topic why matrix algebra for artificial neural network and ML. So simply introduction we have is matrix algebra is the mathematical foundation of artificial neural network and the machine learning. It provides an efficient and structured way to represent data, perform computations, and model complex relations. Almost all modern machine learning algorithms rely on the matrix based operations for the training and inference. So we have already familiar with the matrix and its operations, but here what we are going to discuss, what just we will recapitulate all the basic fundamentals along with how we can write syntax in Python for these operations, how we can write the matrix in Python, then how we can manipulate, how we can do addition, subtraction, multiplications by using NumPy. So here we have the definition of the matrix algebra is the branch of linear algebra that deals with the matrices, vector, and operations such as addition, multiplication, transpose, and inversion. So here a matrix is a rectangular array, number arranged in the rows and the columns. As you can see in this example here, A is equal to, we have these are the element, and the matrix is always represented by square bracket. As you can see here, the left, this is the left side bracket, and this is the right hand side bracket, and all other these are the element inside this matrix. Okay, so the order of matrix is denoted by m by n, where m are the number of the rows and n are the number of the columns. Okay, so here I can use this pen also. Okay, so this is the matrix A, and we denote it by using this symbol. So these are the elements. This is the first row, and all these elements are A11, A12, A1n. 1 is representing the first row, and 1, 2, 3, and so on. These are the column numbers. So this is the first column, this is the second column, this is the nth column. So similarly, we can have this is the second row, and this is the nth row. So the order of this matrix we have is m by n. Okay. Now why matrix is important for artificial neural network and ML? Matrix algebra is essential in artificial neural network and machine learning due to the following reasons. Compact representation of the large data set. Whenever we need to represent the data set, we need matrix. Okay. All the informations which we want to store will be always in the row vector or in the column vector. Okay, so without array we are not able to store the information, so that's why we need matrix and its operations. Efficient computations using vectorized operation and parallel processing on GPU and TPU both, it is required. Clear mathematical formulations of the learning model. Okay, so all type of the operations which we need to perform for this process, we can easily apply all type of the mathematical formulas, just like addition, subtraction, multiplication, scalar multiplication, transpose, and many more. Okay, so in neural network, input, weight, biases, and output are all represented as a matrix. Matrix in artificial neural network, the fundamental computation in neural network layers is given by this equation. As you can see here, Z is equal to Wx plus B. X is the input matrices and W is the weight matrices and B is the bias vector. Z is the linear output from activation. So this function is required when we will train the model or we will establish the model. There will be several steps. So the information which we have, we need the input, we need the weight and biases are there. So in the combination we can have a new function Z. We pass these values for the input layers. So here then after we can have basic matrix operations. So we are starting here the operations by using matrix addition. So two matrices can be easily added only if they have the same order, and C is equal to A plus B. If we have two matrices A and B, their addition will be again we have the same order matrix as we have A and B both are. So matrix addition is commonly used when adding bias values in the neural network. For example, how we can create the matrix and how we can perform their different type of the operations. Suppose that in this example we are importing the NumPy library. So this is the very first statement is used here to import NumPy as NP. Okay, and then we will create the matrix having the order 2 by 3. So how we can use it? We will use only the NP. NP is the abbreviation for NumPy. Okay, NP dot array. So in NumPy we always store the array, and but by using array we want to create matrix. How we can do? See here, this is the functional break for np dot array. Then we have this bracket. You can see this is the left bracket and right bracket of the matrix. Okay, and this is the first row, this is the first row, and this is the second row. So when this is the way how we can create the matrix by using NumPy. Okay, so here what we are doing, we want to print matrix A, then print A. Okay, so both are the same. We can remove this statement. And matrix shape, okay, we need both. First we need to print the matrix, then we are using here how we can check the shape of the matrix. So here what this statement will print this matrix which we created the page and store inside A, and this statement, as you can see here, shape of A, which type of the order of the matrix what will be. So this is the only the string shape of A, and this is the A matrix dot shape. Shape is the inbuilt function in NumPy. This will return the order of the matrix. So when we will execute this statement, you can see by pressing Control and Enter, we will enter Control plus Enter. So this is the matrix. If you want to increase one more row inside, we can do easily. Use here comma. Then I will enter here one bracket, square bracket. Inside I will enter some element 3, 4, 5. These elements I am using here to create this matrix. When I will again execute, you can see we have now new matrix. This is the matrix A having this element 1, 2, 3, 4, 5, 6, then 3, 4, 5. These are the matrix stored inside A, and elements are there. And by using this function, you can see now the order of the matrix is 3 by 3. This is the order, and this order is returned by using this function, as you can see here, A dot shape. Okay, and this is the string shape of A which is appeared at the place on the left hand side of this order. Now next we can have very simple example, row matrix and column matrix. How we can create row matrix? You can see this is the row matrix 1 by n row. Okay, so this function will be always there. Then we have the circle bracket. This is only for the function. Then this is the first row, this is the only row, but we want to print this row inside bracket. Okay, so when I will execute this statement, Control and Enter, you can see this is the row matrix. Okay, and for the if you want to print the column matrix only. Okay, so this is the example to create column matrix. So here np dot array, and see this bracket and this bracket, and this is the left side and this is the right side. Okay, then this is the first element of the column, first row. This is second row element of the column. This is the third element of the column. Okay, so when we will execute, all this will be appeared at this place. Okay, so this will print row matrix and this will print column matrix. So when you will execute, see here, control and enter. Okay, so this is the row matrix and this is the column matrix. So by using this syntax, as you can see here, we can easily create row matrix as well as column matrix. Next, we have very interesting example, matrix addition. So for that, we need to choose two matrices of same order. Only then we can have possible to add the two matrices. Okay, so here you can see I am taking here square matrix. So this is the first row element, and you can see there are two elements in the first row and two elements are in the second row. That means this is the 2 by 2 order matrix, and this is again we have the matrix of 2 by 2 order, and C is equal to A plus B. This is the addition of these two matrices A and matrix B. Okay, so here we want to print the addition of these two matrices. If you are interested to print matrix A and matrix B, we can do also. So here I will copy and paste here and paste here. So first we need to print the matrix A. So here this is matrix A. Okay, then you want to print matrix B. This is the matrix B. Here we have B matrix. So when this is the addition of these two matrices, matrix A plus matrix B, which is equal to C. Okay, so when I will execute, and you can see this is the A matrix, this is the B matrix, and this is the addition of A plus B. So in this way we can easily add these two matrices. You can see the first row from the first matrix and the first row from the second. So when you will add, this will be 5 plus 1 we have is 6, 2 plus 6 we have 8, then 3 plus 7 10, and 4 plus 8 12. Next we have the scalar multiplication in the how we can do. It is again very simple. So the scalar multiplication, each element of the matrix will be multiplied by a scalar, and we can denote it by S. You can see here, suppose that we have matrix A and K is any scalar. Okay, so what we are doing here, we are taking the example, suppose that we have A is equal to 2 4 and 6 8. Okay, and we want to multiply this matrix with 3A. 3A will be equal to, so each element of this matrix will be multiplied with 3. Okay, and this is 8. Okay, so this will be equal to 6 12 18 and 24. So when we will apply this is the same operation here by using the numpy, we will have the same result. Note this one, the same result we can have by using numpy also. So here what we are doing, we are taking this matrix having a 2 by 2 order, in the first row 2 4, in the second row 6 8, and the scalar we are choosing here 3. So scalar multiplication will be scalar product A. Okay, so this will print the matrix A, this will print, and this statement will print the result. What is result? Result is the scalar multiplication of the scalar with the matrix A. And when I will execute, control and enter, you can see we can have this matrix. The matrix A, we have this element 2 4 6 8, but after scalar multiplication we have 6 12 18 24. So in this way we can easily implement this scalar multiplication by using numpy. Now you can come to the matrix multiplication, and matrix multiplication is defined as C is equal to AB. If we have the two matrices and we want to multiply, so this operation is valid only when the number of columns of matrix A equal to the number of rows of the matrix B. So remember this rule. If this condition is valid, only then we are able to multiply two matrix. Suppose that this is the A matrix. Okay, so the element, the order of this matrix we have is 2 4 3 and 3 4 1. This is A matrix, and the order of this matrix we have is 2 by 3, 2 rows and 3 columns. And if we have the B matrix, and B matrix have the number of the, see here, the number of column of A must be equal to the number of rows in B. So here you can see the number of columns in this A are 3. So in the case of B, the number of rows must be 3. Only then we are able to multiply these two matrices. Suppose that here we are taking 2 1 1 3 2 4. Okay, so here you can see this is the 3 by 2 order. So when you will multiply this matrix with A matrix with B, okay, so the new matrix will be 2 by 2 order. Leave these two elements and the new matrix when you will multiply A with B. Okay, so the order of this matrix will be 2 by 2. Okay, so these elements must be equal. The number of columns in A must be equal to number of rows in B. Only then we can multiply A matrix with B. Remember. So now we are doing the same example by using Python. Okay. And what are the applications of this operation? For forward propagation, for feature transformation, linear and logistic regressions, we are required such type of the operations in the machine learning. Okay, so here we can have the example matrix multiplication. So here we are taking A matrix, the elements in A are 1 2 3 4, and that of B are we have 5 6, and C is equal to we have np dot. Dot is in inbuilt function in the NumPy using for the product matrix multiplication. Okay, so here we want to multiply A matrix with B, A matrix with B. So the matrix multiplication of these two will be stored inside C, and here we are using the print command to print this value. Control and enter, and you can see when you will multiply this A matrix with B, and is it possible? You can see the number of columns in A are equal to the number of rows in B, and the product of these two matrices are possible. And you can see after multiplying, the order of the new matrix we have is 2 by 1. Okay, 2 by 1. Because why 2 by 1? Since when you can see the order of this matrix is 2 by 2, and that of this matrix we have is 2 by 1. Okay, 2 by 1. So these are equal. But when you will multiply, new matrix have the order this one, 2 by 1. So here you can see there are 2 rows and 1 column. This is of a 2 by 1 order. Okay, so in this way you can easily multiply by using the dot function if you are required matrix multiplication. Now we have very interesting transpose of a matrix. So in the case of a transpose of a matrix, the rows are column and columns are rows. Okay, and very simple. First we are required to store the matrix. This is the matrix of 3 by 3 order, and first row element we have 1 2 3 4 5 6. So when you will take the transpose, first row become first column, second row become second column. Okay, and this is the function A dot T. By using this operation, this A matrix will be transposed into new matrix. Okay, so this matrix will be stored inside AT, and these are the statement to print the matrices. Okay, matrix A as well as matrix A transpose. Okay, so when I will execute this statement, you will see this is the given matrix A, and you can see the elements in the first row 1 2 3 and second row 4 5 6. And when we will take the transpose, the first row becomes first column and the second row become second column, as you can easily observe the transpose of this element. Okay, next we have very interesting element wise operation. Element wise operations apply functions independently to each matrix element, and these operations are widely used for activation function, loss computation, regularization techniques, and many more. So here we have the very simple example. First we are talking about identity matrix. So I is inbuilt function, and by using I we can easily create the identity matrix. But here if you are identity matrix is always square matrix, so either it will be 1 by 1 or 2 by 2 order, 3 by 3 order, 4 by 4 order, and so on. So identity matrix will be always square matrix. So if you are entering here 3, so this will be the identity matrix of 3 by 3 order, and when you will execute this cell, okay, so when you will execute this cell, so this will be 3 by 3 order. And if you are taking here I'm running, you can see the diagonal elements are 1 1 and other elements are 0 0. So this is the example of identity matrix. If you are taking here 2, so we have this matrix 2 by 2 order 1 0 0 1. If you are taking here 5, okay, so this is the identity matrix of 5 by 5 order, and only the diagonal elements are 1. Okay, this is the example of 0 matrix. If you are taking only 4, this will be the only zero matrix. Okay, and if you are required 3 by 4, 3 comma 4, so this is the 3 by 4 order zero matrix. And sometimes if you are required square matrix, so we are required 4 by 4 order. So in this way you can easily create the zero matrix whenever it is required. We can do. Next we have is the element wise multiplication or Hadamard product. Okay, so what happen in the case of this type of the multiplication, you can see in example A, in matrix A, we have this is the 2 by 2 order matrix, and this is also 2 by 2 order. So when you will multiply, we have new matrix that is also again same order matrix. So when we will do element wise multiplication, okay, so 1 will be multiplied with the 2, okay, and this 2 will be multiplied with 2, 4, this 3 will be multiplied to 2, 6, and last element 8. Okay, so number one, the order of these two matrices are same, equal, and the element position or the element order from the both matrices are same. So first element with the first element, second with the second, and third with third, fourth with fourth element. So this type of the multiplication is known as element wise multiplication, and this is the notation A product B. So by using this one, we can easily get the element wise multiplication, and also this type of the multiplication is known as the merge product. Okay, now come to next definition. Element wise operations already we have discussed, but in here we have introduce some more examples. Element wise operations are operations applied independently to each element of a matrix or the vector. Unlike matrix multiplication, there is no mixing across rows or the column. Each position is processed on its own. These operations are fundamental in artificial neural network and machine learning, especially for the activation function, loss function, and masking or regularization. So here this is the definition. You can see here we have a matrix Aij order, this is the Bij element, and the order of the matrix we have is by n. So when you will multiply these two matrix, we have Cij is equal to Faij Bij. So this is the function, just we have the element wise operation. Okay, F is element wise operations. So we can have addition, we can have subtraction, we can have multiplication, we can have element wise division. So all these operations we are discussing here one by one, and this will have more understanding for you about these. So here very first we are checking here element wise addition and subtraction. So here you can see C is equal to A plus B and D is equal to A minus B. We have two matrices of same order, and we will add and subtract them. So here we are taking these two matrices. A matrix have the element 1, 2, 3, 4, and that of B we have are 5, 6, 7, 8. So here we are taking the addition of these two matrices A and B, and print A plus B after this is the operation on these two matrices. Okay, this is the sum of the matrices, and sum will be printed here. Similarly, we have the subtract B from A. So we will subtract this B matrix from A, and A minus B. This is the operation which we have applied at its place. When we will execute this shell of the statement, we have these inputs as you can see here. Okay, so this is the addition of the two matrix, and this is the subtraction B from A. If you want to execute, we can do yes. So 6, 8, 10, 12, this is the addition of A and B, and A minus B will return the subtraction B from A. Minus 4, minus 4, minus 4, minus 4, each are minus 4. Then we have the element wise multiplication. Of course, we have discussed in the previous example, and the similar type of the example we can have at a space also you can observe, but the process is same. Each element of matrix A will be multiplied with B. Okay, corresponding element. So we have this example. The element of A we have 1, 2, 3, 4, and that of B we have are 2, 2, 2, 2. So when you will multiply element wise, so first element with the first element, second with the second, third by third, and 4 by 4. So this is the process of the scalar element wise multiplication as we have discussed in the previous example, and this is also the similar type of the example we have choose at this. Now we can have element wise division. So the process will remain same as we do for the addition, subtraction, multiplication. For division also we have the same case, but each element, suppose we have this A matrix, this is the B matrix, and we want to divide A by B. So this element will be divided by 2, and 10 by 2 we have is 5. Okay, and this element will be divided by 4, this element will be divided by 5, and this by 8. So in this way we have new matrix after division. So each element will be divided with respect to the same order element from the second matrix. And if you want to execute this statement, the code which I have written at this place for element wise division, you can check here and you can manipulate, you can choose some new examples, you can manipulate these values. Control plus enter, so you can have this value. Okay, 5565. Next we have very interesting element wise function. Okay, so in artificial neural network and machine learning, non-linear function are applied element wise to the matrices, and very famous we will use here ReLU function, which is defined here. ReLU function is defined here is maximum of 0 to x. Okay, so x is the maximum value from this one. So when we applied the matrix value, operate on each element independently, and you can see here z is equal to np dot array -2 0 3 1 -7 4. So this will value np dot maximum 0 to z. Okay, so when you will execute, and you can see only the positive values are there, 0 0 3. Okay, and for the second, negative values are absent. Then we have the sigmoid function, and also this ReLU function we will pass through sigmoid function. The sigmoid function is simply defined as, you can see there are various type of the activation function, and sigmoid function is one of the example. Okay, we will discuss in very detail in the coming sessions, but here I put only one example so that you can be familiar how we can write the Python code, how these matrices operations we can implement. Okay, so here you can see the sigmoid activation function is defined as 1 upon plus 1 plus e raised to power minus x. Okay, this is the sigmoid function, and symbol we are using here sigma. Okay, this function is applied element wise to neural network outputs. See here, sigmoid is equal to 1 by 1 plus np dot exp. exp is inbuilt function in numpy, which is exponential function. Minus z, here you can see the power is minus z, that's why we have minus z. And what is z here? We have this matrix. Okay, we will pass this matrix through this exponential function and print sigmoid. So when you will execute, this will compute all the values of the matrix and will return at this place. Okay, so this is the matrix algebra in the machine learning model which we have discussed here, and the examples which we are trying to play will help you. So the matrix algebra plays a crucial role in various machine learning model, including linear regression, y is equal to xw, logistic regression is their principal component analysis, PCA. Okay, support vector machine and recommendation system. So eigenvalues, eigenvectors and matrix decomposition techniques are central to many of these models. We will cover the eigenvalues, eigenvector and matrix decomposition in the next lecture. We are not covering here. Okay, so here you can see the example 10, matrix in ANN. Forward pass example is here. So first we are required input features. So 3 features, 1 sample we are taking here. These are 3 features and 1 sample only, 1 2 3. Okay, then this is the w is the weight function. So weight matrices is there, np dot array 0.2 0.5 minus 0.1 0.7 minus 0.3 and 0.4. So 2 neurons are there and 3 inputs are there. Okay, so this is the matrix 2 by 3. Then this is the Bayes vector, b is equal to np dot array 0.1 0.2, and this is the linear output np dot w comma x. So w is there, x is there, so we will take the element wise multiplication, then plus b. Okay, here is the matrix multiplication. Sorry, a dot is used for matrix multiplication, not for the element wise multiplication. Okay, so this is the matrix multiplication, then plus b. Okay, so this is the linear output when you will pass these values, and when you will execute, control and enter, you can see here neural network layers output 1.5. Okay, so in this way we can have all these operations. Advantages of matrix based computation. So we are going to very close to the session. So the use of matrix algebra provides several advantages: reduce computational complexity, faster execution through vectorization, scalability to the large dataset. When we have very large dataset, we can easily execute, and scalability. Okay, compatibility with the hardware acceleration, and mathematically clarity and consistency. So all type of the operations which are required for our data set, we can matrix operations play very important, and by using numpy we can do all type of the such type of the calculations which are required for our purpose. So now we are going to conclude our this lecture. Matrix algebra forms the backbone of artificial neural network and the machine learning. A strong understanding of the matrix concept and operations enable efficient model implementation, better operation, and deeper insight into learning algorithm. Mastery of matrix algebra is therefore essential for anyone working in artificial neural network and machine learning. So thank you to keep in touch with the entire lecture. In the next lecture we will talk about eigenvalues, eigenvector, and decomposition. So stay connected. Thank you to see this lecture.